Good morning. Today's Monday. Welcome back to school. Give you a chance to watch this video talking more about growth models. This time we're going to focus on the formulatic side of it, or the explicit formula side of it. Start with this bell ringer. As of February 10th, as of February 2010, the swine flu concerns seem to be lessening. Since its inception, 70 million people were vaccinated and 55 million people contracted the swine flu and recovered, meaning that their bodies created some level of immunity on its own. Collectively, this has implications for the resistance to the general public, and that the general public now has to that particular strain of the virus. What mathematics is involved when epidemics or pandemics occur? Is there a functional model or rule that is realistic that can be applied to such cases? And how might you simulate such an occurrence? All right, so we're going to talk about that. And in the future, in the very near future, we're going to actually do a laboratory that actually is a good simulation of that. But until we get into this lesson, it's kind of hard to describe what it is we're discussing. We're talking about the logistic curve. We know that when we looked at that specific growth of bacteria, if it's unmitigated or if it's unrestricted, it will go on and move in an exponential curve. But if it is restricted, if we have some way to contain it, like we quarantine a certain number of people, or we put the bacteria in an agar dish that has only a certain square millimeter area, we can limit the growth. Anyway, that's how we do it. And we'll look at that logistic curve through this entire lesson. So what makes life great? See, this past week on Thursday and Friday and Saturday morning, I went to Galveston with the SCCLA team, Culinary Arts, Mr. Torres's crew, a couple of y'all in my class. We're in that group. We had a lot of fun. Those of you guys are not involved in certain things that take you out of your comfort zone, like cooking in front of people that you don't know and let them judge your ability to do so, you might consider doing something like that. It was a lot of fun. So, H1N1, 2 letters and 2 numbers. They're memorable at the most recent and perhaps greatest public health concern of this decade. Now, that decade was almost 2 decades ago now. So we're talking about the first decade of this millennium. 2000 to 2010, swine flu was a big deal. To put that in perspective, the coronavirus we have right now is 10 times as deadly. Just giving you an idea of how bad that is. Fortunately, we don't have a lot of outbreak here in the United States. It's pretty much limited to China. The outbreak of this strain of influenza, as most similar outbreaks, can be simulated using mathematical techniques and model you are familiar with. The simulation of this activity may create duplications or repetitions. For example, 2 people may both infect the same person. Okay, what are other possibilities of duplications, repetition, and random number generating based simulation? Well, that mimics the way the public society works, if you think about it. If you're sick, you come into contact with people that aren't sick, that are sick, or that have been sick. May come into contact with an already infected person. An infected person may reinfect himself or herself. And that has happened to me, and it probably has happened to you too. These duplications or repetitions are a desired aspect of the simulation because they signal the change from one stage of the simulation to the next stage. And what we're talking about here is we come into limitations, and that's what we're talking about. Now, if I were in Coach Primo's class, I'm talking about myself in the third person. If I were in my own class, I would understand these 4 stages of growth labeled in this particular curve. This curve is called the logistical curve, and there are 4 parts to it. The 4 stages of growth in a logistical curve, or limited growth. The first is initial. It's slow to grow. And then exponential, that's when it starts to gain momentum. We call that the snowball effect. It really gains momentum until we start to get closer and closer to the limit. And we get about halfway to the limit, it dampens, and it doesn't grow as fast. As a matter of fact, it starts slowing at an exponential rate. The closer and closer they get, the slower and slower it gets. until we get to a point of equilibrium. And equilibrium is a point where we're actually so close to the limit that there is no or very minimal growth. So those are the 4 stages of growth. What's happening with the spread of the flu virus in the graph on the previous page? The virus is growing slowly at first in terms of numbers of people infected, followed by more rapid growth for a period of time, then leveling off a bit in numbers of people infected. You think about it, if it goes unrestricted, there is a limit to the number of people it can infect, and that's the population of the world. If we do have an epidemic that spreads across the world, you can only infect so many people, and some people are going to survive, those that are immune or those that gain immunity through the sickness. And that's just how sicknesses work. You're going to imagine a total population of 100 individuals, each numbered from 0 to 99 in the hundreds chart, and that represents an individual with a number of 0 used to portray the original host. Use the hundreds chart to keep track of the infected individuals by crossing off their number on the list as they become infected. So how does this work? The original host infects a person represented by a randomly generated number. We'll generate a random number between 0 and 99 using the graphing calculator or some other random generating tool, and we'll mark that person in the chart. So how do we do that? Let's see. Okay, so we're going to go to the math right here, math, and then we're going to go to probability. Let's scroll over to probability. Now, I want to use a very specific kind of random number. I want some parameters. I said I wanted 0 to 99, right? So let's go down here to random integer, and it's going to give us some options. The lower we want 0, the top we want 99. I don't know, I guess that's a number of random numbers we need. Let's just go 1. The first number is 90. So we would go back to this chart right here, and we would scratch out the number 90, okay? And then we would hit random again, and it would be 14, and we'd scratch out 14. And we would do this for every day. Okay, mark that person in the chart. Day 2, the 2 infected people from day 1 now infect 2 people, so generate 2 random numbers. We'll start with someone in this chart as infected. Okay, so let's say it's 0, then 90, then they each infect 2 people. So as you can see here, we'll do that all the way up to day 6. Now, in this simulation, which I've actually done, this is simulated data. We'll continue to simulate the rest of the days, completing up the table of data up to day 6. So the number initially people infected was 1. We infected 1 new person. Total infected people is 1. That's day 1. Day 2, we had 1 person infected. We infected 1 more person. That means we have 2. Day 3, we have 2. We infect 2 new people. That makes 4. Day 4, we have 4 infected people. They infect 4 people, and that's 8. On day 5, 8 infected people infect 8 people, and they infect 16. Well, look at this. On day 6, they only infected 13. Well, how do we do that? How do we know that? I think it has to do with the process. Let's go back to the process real quick, see what it says. So on day 6, we have some replication of the numbers we chose before. So out of the 16 people that were infected, only 13 were not already infected. 3 of those people only came into contact with people that were already infected. And that explains why that process happened. How is the number of infected people growing, and what function model would you use to model these data? The number of infected people is growing exponentially, and you can use the exponential function model to model this growth. And you can see this on your calculator. We put this into stat edit, and this is what this particular graph looks like. It does model an exponential function. As a matter of fact, we use our graphing calculator. We can see the graphing calculator starts with the initial value of 0.17. Actually, it's close to 0. And we're growing at a magnitude or a clip of about 2 to the x power. That's our exponential growth right there, okay? So what are the independent and dependent variables in this model? Obviously, The day is completely independent of the number of people that are infected, and conversely, the variable that is dependent is the total number of infected people. You can't infect more people as long as days don't go by. All right, graph your function rule over a scatter plot of 1 to 6 days. How does it fit? It fits pretty good. We put the function rule on y equals x, and it looks like it hits every single one. However, there's an issue. We need to predict the number of people that are infected by day 10. We only had 100 people. How can we have 151 people infected? So if we follow this particular function, it's not going to work. It's problematic, and that's part of the issue. This is problematic since there are only 100 people in this closed environment. It's only 100 people that are in quarantine, right? So we'll add 7 and 9 to the table of simulated data, and notice that the number of people that are infected are further and further away from the total number of initially infected. And that's merely because what's happening is we're running out of people to infect. So we get an idea of where our process is coming into an issue. It is no longer exponential. Remember the 4 stages of growth in a limited environment. So we'll record the day through 15. Notice that here in the last few days, there are only a few people left to infect. So by day 16, we'll have the last person infected on day 16. Obviously, somebody is going to come into contact with him. It's possible they may not. It may stretch on and nobody gets infected. That guy decides to keep to himself. He may stay uninfected. So there's that possibility. So let's move on. You should recognize this graph from the work on the last lesson in recursion as logistic graph. And we're going to reuse the regression capabilities of the graphing calculator to determine the function rule that best fits the scatter plot. Then graph the function rule over the scatter plot. Well, check it out. Well, how do we do this? So let's look at our TI calculator, stat, enter. Let's put some information in here. So now we have our information in here. This is the logistics graph. We want to see what it looks like, and we need to find out what we can do about how do we determine what it is. Let's turn our stat plot on. Let's look and see what it looks like. Okay, it's on. Zoom 9. Well, there's our curve. It looks very similar to this. But how do we determine what the actual formula is for this? Let's go to stat, calc, and there's a regression function for logistic. Check this out. Just a few down from exponential regression, B is considered logistic. It uses the information from L1 and L2, and it calculates a best fit function. Once it gets that information, we have our function. All right, it looks like I've got it in there now. So when I graph, let's see what it looks like. And that's much better. Okay, so how well does the function rule fit the data? Very well. The graph of the logistic function displays asymptotic behavior. What is the meaning of an asymptote, and why is the graph in fact demonstrating this behavior? So let's think about it. What is an asymptote? We learn in Algebra 2, what's the opposite of an oval or a circle? Hyperbola. Those hyperbolas have asymptotic behavior. The curves never reach a certain point, and that's something we can discover. The same thing, I believe, we can discuss with a few other things, but that's the major one we should consider. An asymptote is a line that continually approaches a given curve. It does not meet it at any finite distance. Data and resulting function rule logistic display asymptotic behavior because of the limitation of the total and the density of the population size. The value of an asymptote is referred to as the carrying capacity. So in this case, the carrying capacity of a quarantined group of people is the number of people. The carrying capacity in an area in an agar dish is the total number of bacteria that can be infected that will fit inside that area. I'm going to launch you on this coronavirus. There's a lot not known about this new virus or how it spreads. The knowledge is largely based on what is known about similar coronaviruses. There are lots of coronaviruses. I did a little research on this. They're common in a lot of different species of animals, but rarely those coronaviruses infect people and then spread between people. Now we have one called the 2019 NCOV. That's the most current one because the outbreak started in 2019. There's much more to learn about transmissibility, severity, and other features associated with this new virus, and investigations are ongoing. They're going to further inform through risk management, and you can read more. These links will be available in the actual slideshow, which I'll keep available to you in classroom. In the meantime, y'all be sure to go in the Google Classroom and do the assignment in the Google Classroom. It is due today. Thank you very much. Have a great day. Be blessed. And